So that
So I think we'll give. Okay. So it's, is it on? Okay. Yeah. We'll give everyone a few more minutes because the announcer person for the room is not actually here yet either. So I don't know if I'm supposed to just start or go, just improvise. But so just a couple more minutes. Cool. Well, the windows. I don't think it's getting any better. So I'll give them one more minute to see if anyone comes How's the dog? Um, give everyone one more minute to see if any of the announcing people or the mixing people come in, and then we'll get started. Okay. So let's get started now. Welcome to Rock the Cashbox. Unfortunately, I didn't have a better name. I wanted something clever, and in the end, what we're going to be talking about today is practical, hands-on protocol analysis. While it's cool and everyone's probably here because the words ATM hacking were in the title, there's real-world applications to looking at protocols from this level and working with protocols and trying to reconstruct them, especially when you have old protocols. See how they work, see how to reconstruct them so you can better design, defenses, and in the future, design better protocols. So about me, I go by Spicy Wasabi on Twitter. I'm a security researcher of mostly embedded devices and IoT, so ATMs fall right in that category. I am also a perpetual volunteer. I work on quite a few different events, mostly competitions. One of them being the Collegiate Cyber Defense Competition, and the other being the Collegiate Pen Testing Competition. While those are a lot of words, both of them are both college competitions for students to participate and gain real-world skills. As an organizer of those events, I get to be essentially the game maker and build the challenges and build the competition into something that actually exists. So that brings us to the next point. This was built for a competition called CPTC, the pen testing competition, and students were required to build or maintain, or not maintain, defend a bank, and pen test a bank. Sorry, and as part of that, I was working with another guy. His nickname is JRWR, and he works and lives in Rochester. This was a national building event for this ATM work. And without him, I don't think any of this would have been possible. So I really appreciate being able to work with him, and I hope I get a chance again in the future. But I'm sure you're not here to hear about me. You want to hear about rocking the Cashbox. So what are we going to be doing here? Well, one, we're going to be working with ATMs, and inside an ATM is something called the Cashbox, which actually contains the money. And so we're going to make the ATM eventually just dispense money. And so that sounds really scary, but what this talk isn't is we are not modifying the ATMs. It isn't about hacking ATMs. It isn't about modifying the firmware or dumping the firmware and figuring out how to make it do something that it isn't supposed to do. We are only doing pure protocol analysis and working on a closed environment. This stuff does not directly go into a real world, and if you were doing this where it was a real ATM that's still in service, that would be very bad. The reason primarily we built our own protocol processor for this stuff was because we wanted to make a fake bank where we could have students have to experience money getting dumped from accounts and have to deal with that situation. If it was real world, a bank would probably not be very happy with that. So this is meant for the best reasons, and we're specifically talking about that protocol work. So let's talk about the protocols. Well, these ATMs are very old. They were released in the early 2000s. I think they stopped getting developed in 2004. So we're talking a Windows XP era system at best. Well, in fact, these systems don't even run Windows XP. They're running Intel 16-bit microcontrollers that provide the entire operation for the ATM. And the ATMs may be 15 years old, 16 years old, but the protocol they use is even older. It's almost 30 to 40 years old and has not been changed much in any way since then. And this probably gives you an idea why this is such a problem, is because this protocol is still in use today. These ATMs still exist, and if you see one, they are running this same protocol, or one of its variations. So what we're going to have to do instead is a little gentle persuasion. As I said, we're not hacking the ATMs directly. We're not using some exploits to get to a shell on the ATM. What we're actually doing is persuading the ATM to respond to us and do what we're needing it to do. So, again, back to the background. The students were tasked with pen testing a bank. The bank had many simulated systems, including databases, accounting software, and everything was custom written that the teams had to evaluate and work with. In fact, in the audience, there's actually some of the competitors today, so hopefully they'll get a chance to see the work that went into this. But we thought, wait, what about getting ATMs? And it turns out you can actually just go on eBay and buy pretty much anything. You can buy voting machines, you can buy ATMs, you can buy payphones. There's a very weird world in eBay of buying pretty much anything, and it's readily available. And it so happened we found the deal of a lifetime. For less than $500, we could get 12 fully functional ATMs. The only thing we had to do was pay for shipping. Well, good news, you can rent a truck. And so an adventure started. We had to somehow get 3,500 pounds of ATMs over 1,000 miles from Ohio to New York and get them there in working order. Well, that was no small feat. ATMs are heavy, and so that makes turning a little bit of a scary situation. You will notice in this picture, I know it's a little cut off, if you do a count carefully, there's 4 ATMs on one side and 3 on the other. That makes it a little challenging because what does a sharp turn do? Can cause you to tip. And that almost happened to the people driving these ATMs in. But luckily for us, only one ATM did not survive the journey, and we were able to get them into their new home. So with these ATMs in our presence, we had to figure out how to make them work. There's no documentation. We weren't official resellers of these ATMs. We just bought them. So we had product manuals. We had product informations, tech sheets, but that doesn't really talk to us about how the ATM works. What it does say is go contact a local vendor to get your ATM hooked up, which is great and also useless. So, we wanted to see what they could do. So this is the beautiful noises of ATMs all plugged in at once. Wonderful dial-up sounds. And so we had to figure out how these things worked. Oh wait, why is there 2 slides of the same one? Okay. Oh well. But the thing was, we didn't know how they worked, and they were in really bad shape. For ATMs to be that cheap, you have to imagine there's something wrong with them. And there was definitely something wrong with them. These all came, as we found out, because they still contained all the information that they were last set with. They came from Waffle Houses and gas stations, and there was no exception. So most of these ATMs were absurdly sticky, and a few of them even contained rats and other leftovers that were absolutely disgusting. One of them actually had wrappers inside of it. Somehow in the base where the safe is, there were wrappers and old, just leftovers just in there. It was awful. So we had to sanitize these quite a bit. And then once we did that, and we were not afraid to touch, we weren't worried about touching them, we had to figure out the first task. It was a very simple requirement. Communicate to the ATM. And that seems easy, but it really isn't. So it turns into just a few things. So you have these ATMs, and you want to make it as realistic as possible. So that means you can't just replace the guts with some Arduino controller and say, okay, it's an ATM. And if you did that, how would you get all the other components to work? And you want to make the teams connect to their ATMs directly and have what they're doing affect the actual outcome of the ATMs. So if someone steals all the money from a fake account, you want the ATM to show the balance is 0. So you have to make it realistic and work. So we had to start getting a little creative. We saw that there was a modem line, actually there's 2, and we had to start figuring out how it worked. So here's one of the pages from the product tech sheets. And as you can see, it really tells you nothing. It says here's a keypad, here's a printer, here's the cash dispenser, communication, and you can see it supports up to Ethernet LAN capabilities. Of course, none of them really did. And if you want to get that upgrade, it's $1,000 per unit to get the upgrade to Ethernet. So we decided, let's get creative. I'm sure dial-up isn't that hard. People were using it for years. And that's where our adventure started. So to do that, we started plotting out, if you're looking at a piece of hardware that you don't understand, you don't want to just jump into it and say, okay, let me see how this goes. You want to identify the components. So the We did. We went through piece by piece and tried to identify the ATMs. And there were some interesting situations that we found while we were doing this. First, the pin pad contains the crypto keys, which is a very interesting situation. There is a reason, JRWR explained it to me, and I forgot, but there is a reason for having the crypto keys on the pin pad. And it's in case someone tries to tamper with it, it'll become unusable. I believe it's something along those lines. But it's actually a documented feature and a standard for how to implement this stuff. The printer controller also has the same 16-bit microprocessor. And the dispensers, there was quite a bit of variety. What it turns out is that they use commodity hardware. This is like a building block, like building your PC. You want to swap out the graphics card or something like that. Instead of graphics cards, though, they have printer spoolers, they have card readers and things like that that you can just easily swap and can speak the own protocol. They're not using PCI bus or PCI Express. In fact, they're only using serial. So that gives you an idea of how much bandwidth these things actually support over these protocols that they're communicating over. And they don't change because you have to use these year over year. Some of them the silk screen prints were from 1985. So these things are very old and they're still used. These are actively manufactured. So here's the first one. You can see the core, the main processor, and up top, the big disattached piece is the modem. In the front, there is the serial ports. It looks fairly standard. And then we found a couple like this, and we still don't know to this day what it is. So you'll see there's the main processor. There's some other changes to the board. It's a different revision. We're like, okay, that's not too surprising. On the top, soldered right on top of another chip, is this little board on top. I don't know if it's clear, but over here, there is a separate board just on the top, just sitting there. Has its own microcontroller, has its own clock, has its own memory, and some dip switches. We really couldn't figure out what this was for, but on some of the ATMs, it was soldered directly onto the existing board. And so that was kind of interesting. So we don't know what that means, but it's also not documented. It seems like people are just repairing these with whatever they can, and sometimes that means just soldering on like an attachment piece. That's what we think, at least. So again, we're trying to make the ATMs work. So we discovered all the different components, and we're like, okay, we now know roughly this is a dial-up ATM. It's going to be using it's not running anything with Windows, so we can't analyze the protocol on there. We have to figure out how this thing communicates, and we have access to the menu interfaces. And all they talk about is either a localized payment processor or a remote payment processor. So how this works is ATMs, especially these dial-up ones, you don't need a very fancy communication protocol. Hopefully it's encrypted, but you don't need a fancy one to communicate to a local payment processor. And in many cases, what they'll do is they'll have a local payment processor for an ATM, and that's sitting behind, wherever inside an office, and that connects to the internet. And then that connects to whatever payment application and protocol that you want, whether it's web-based or anything else. That's an actual payment system. Or you can send out to a remote site where you actually have a bank of numbers that you set up and connect to. And those are actually services that you can subscribe to, and they'll take your payment and also set in the fees automatically. Well, the problem was we didn't have either of those. And so we had to figure out how to do this. So we were like, okay, let's emulate a local payment processor. That can't be that hard. Well, of course, we didn't have one. So as it turned out, we actually got a local payment processor the day before the competition started. But it turns out it supports only SSL, not TLS, so very good. And it requires another protocol to communicate to the internet, so we couldn't just analyze it when we tried. So we left that alone, but we want to emulate that as much as possible. So the plan was to take the ATM, connect it to a PBX, which would emulate to a Raspberry Pi, which would emulate the payment processor, and then send that to our cloud and our competition network. Well, the reality was a little more complicated. So we had our dev system, which connected via a jump box to a local Raspberry Pi, which connected to multiple USB modems, which then connected to PBXs, which then connected to the ATMs. Very simple. And it was not simple. Sometimes this system, this complex web of connectivity would break. And because I'm working on the West Coast and the ATMs are on the East Coast, and to make it even more complicated, they were in a storage building. we would have to sometimes, I'd have to call up JRWR and be like, hey, I accidentally crashed the ATMs again. Please go reboot them. So it was quite a hands-on process, and sometimes because of time zones, that would be like 6 p.m. or 8 p.m. his time. And we'd be like, okay, let's just reboot it and start working again, and have to start all over again. But, you know, it turns out it was just luck that we had, JRWR had experience with PBX systems. He actually had an old PBX system lying around, and we had USB modems. So we realized that we could actually make all the stuff start working and just simulate and start listening on the USB modems to what was being received. We had no idea what we were going to get or what they were saying, but we wanted to try. So the final implementation looked like this. We had multiple PBX systems with a bank of ATMs connected to a single PBX, which then connected to a Raspberry Pi, which then connected to a relay server. And this obviously sounds very complicated, but this allowed us to connect and bypass certain firewall limitations that we had, and it allowed us to keep all the ATMs on the same network and troubleshoot very quickly. So as I was saying, we rediscovered a lot of stuff during this endeavor. We rediscovered time sharing because we only had 2 ATMs connected, and so if we're both working on the same ATMs at the same time, it's not going to work. They're going to dial on each other. And we also rediscovered real @, commands, not the @modem commands you're used to with cellular modems. These are real @ commands, where you have to do auto redial and auto reconnect and setting the mode of the communication. It was a little bit of a lost art, and it turns out that working weird hours is really hard for getting something working. So we actually spent many Saturdays where I would get up at 6 a.m. and be working until, you know, really late, and out on the East Coast, he was also working, and he would be in the actual warehouse working with the ATMs, and I'd be tinkering with the systems trying to get them to work. So time sharing, it works. But for the protocols, it turns out US robotics still exists in a little sense, sort of. And they sort of exist, not very good, but they have some documentation on their modems, and their modems are pretty good. They were the standard for years. So their documentation is fairly well followed through by any implementation. So it turns out to get the modems to auto answer, you do ATSO equals 2. Simple. That's really clear. And so we got the modems to auto answer. We got the ATMs to auto dial. And so we started getting this repeated dialing process that we could start looking to decode the messages. And it was interesting because we couldn't recognize anything. We set the ATMs in their menus to automatically set all of the values to be zeros. We figured zeros are going to be easy to detect. They're going to be a big pattern, and we'll be able to see when a different type of data changes. We don't care what the actual message is, as long as we can see a big chunk of zeros, we know when the message starts and what the protocol is going to be in the end. Well, the problem is the ATM never really responded. We sent data, we sent commands, we thought we were sending the correct messages. It just didn't work. And then we discovered some challenges. So, you know, we started with PySerial thinking, yeah, Python's going to be a good development environment for this. And during one of our endeavors, we actually switched to PHP for a while because that actually was more reliable. And I'll never forgive myself for that, but it actually worked a lot better for testing. And then we went to Screen because we thought, okay, maybe we need an interactive serial processor. And we're like, okay, Screen's not really working for us. Let's try Minicom because that's really designed for modems. And then we found Intercept T2i, this random GitHub project that this guy made that allows you to take a serial port and split it off to a file, capture all the raw data, and then forward it onto an actual application. So this is when we actually started getting our progress. So serial's unreliable. Sometimes messages don't come through in entirety. If you're not listening at the right moment, you've just missed the message and you have to wait till the next cycle, which means the ATM has to reconnect or get rebooted. And there was no clear pattern. And what I mean by patterns is you're trying to find in a bunch of hex something that looks like it's repeating so you can find the correct messages. So we thought, maybe is it encrypted? But if it's encrypted, how does it know what the encryption key is? Is there a preamble or anything like that? So this is what we started doing. And this is just a quick screen grab I got. So when we're doing the work, You're looking for at an unknown protocol and an unknown message. You don't know what you're looking at. And the goal is to identify the same messages and see what they are and maybe find in between patterns. So here you can see the 0D, 0A. Okay, I found one. Then in the next message it's also there. But then all this random data. I found a 9-4. Okay, that's good. And then I found this whole string of 0D, 0As. You might be wondering, the messages look very similar, right? Like the 0D, 0A. So we had a big oops moment that we kind of spent a couple weeks working on this and then didn't realize what we'd been seeing. And this is the ASCII decoded version of the hex that you saw above. And it turns out we had been looking for decoding the modems. We had gotten the modem messages, and what we were actually seeing as repeated patterns were actually the ring, 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 connect 9600, no carrier, and then repeating. So we spent a lot of time trying to decode that. And when you get into the zone, you have to think about that when you're looking at message processing. It's easy to fall into like, well, we have to decode this complex message. In reality, if I had just checked ASCII, we would have seen this weeks before and not stumbled on the same problem. But in that message, there's actually a bunch of hex. And so once we found the actual hex, we realized, okay, maybe there is a message here. Something that isn't actually ASCII because it's still not decoding, which is a really good feeling when you've messed up that badly. So what could those 77s be? Now in protocols, there's something called a preamble. Many protocols have this. And what it'll be is a repeating sequence of numbers, or bytes, I should say. And you're trying to find that it differentiates noise from actual data. And here in my graph, you can see actual data starts at the very end where the question mark is, at the far right side. And at the beginning are different types of message where you're sending 77 hex, and you can see how it repeats and you can identify that, or sending a bunch of FF and finding the change. So we started on the theory that maybe what we're actually seeing is a preamble. And we kept getting stuck. And it just so happened that when we were going through it, we were looking through text sheets, and we found some old manuals on provisional guides on what protocols were used. So we thought, okay, maybe we're onto something. So we started switching around the system, and we looked at the fact that there's different modes. There's standard 1, 2, and 3, which tell us everything about the protocols. And it turns out standard 3 is what we actually implemented. But we didn't know. And EPS link and ST3 plus link, we still don't know what those are. They're Googleable, but they're not described. And that's the problem, is a lot of this payment stuff is not described for presumably obvious reasons. They don't want to share it because it's a licensing thing. I don't really know, but we just couldn't get a hold of it. So from the documentation, we realized the modem has to operate. We had to set the modem speed to 2400 baud, 7 bits of data, and 1 stop bit. And for those of you who have actually worked with old serial protocols, I'm sure that makes perfect sense to you. But for someone who's never worked with old serial protocols, it's a little bit confusing. I have clarified that because it said ASCII plus 1 stop bit. Now, it turns out, and I'll get to this in a minute, ASCII is not the same as it used to be. So we'll get there. But it says even parity. The start of the message is an STX character. There's an ETX character, an LRC, and then an ENQ message. So these are all ASCII control characters. We were easily able to identify those, but we didn't see them. And so the control flow is supposed to work something like this, where the ATM dials out, it gets an ENQ, sends a request, gets a response, acknowledges the response, we send an end of table message, and then we disconnect. That's if it's working. Of course, it never was that easy. So based on the documentation, we need to send an ENQ to get the ATM to start transmitting when it connected. And it still replied, but after some delay. There was a pause of about 30 seconds. And I'm sure people here are starting to wonder, what was the 30 seconds? And it turns out the 30 seconds was a failure. It was timing out because it wasn't getting the right message. But the protocol is based on VisaNet. And there's an old FRAC article we found when we discovered that it was based on VisaNet from 1994. This FRAC article in it, and this is how classic this frac article was, is it was advertising DEF CON 2 and saying how great a hacker conference it would be. Bring all your friends. And it was a lot cheaper back then too, but it said the article was written in such a way that this was just common knowledge, which it really isn't. But it said, as you are very well aware, you have all your dial-up numbers, and when you send an ENQ, 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 you will get an actual response from the VisaNet merchants. Clearly. So we tried sending ENQ, 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 and it spit back data. Immediately. No delay this time. The problem was, again, if you look back to the control flow, where is the ENQ, the ACK, or the NAC? Well, I'll let you decode the bytes by hand, but they're not there. And so we started getting worried. We put the ATMs, we verified that they were in single mode, because there's a batch mode where it can send bulk messages. So like if you do a transaction, it'll say, good job, I've done your transaction, do you want to do anything more? And then you say yes, and then you keep saying yes. You've probably seen this at ATMs. What that does is when you press finish, it actually transmits all the transactions at once. I don't know when this would be useful these days, but that's what it was designed for. And so we put them in single mode, so every transaction is a new dial-up transaction, and it sends it. So we voted for the simpler method, but was it the parity bits? So when it said ASCII +1 parity bit, we thought, okay, ASCII's 8 bits. Right? 8 bits of ASCII, you have all these bytes and you just type it in S. No, I see a lot of heads shaking. And this was our mistake. We'd never dealt with good old parity bits before. And it's something that when you Google parity bits, a lot of people have a lot of opinions and a lot of different answers. I don't know why there's so many different answers, but there should be only one, but apparently not. So we tried shifting the data. We said, okay, it's 9 bits. And we're going to frame it 1 parity bit plus 8 bits of ASCII. That yielded in some even worse data. Then we thought maybe, what's going on here? So breakthrough, we found the actual correct representation of parity bits. And as you can see, ASCII is actually 7 bits. In modern systems, the 8th bit is either unused or just used as like a buffer. But in older systems, it was actually used as an error detection. So it would be even parity if it was an odd number of bytes before it. So you can see 0 through 6 bits. If that was odd, the 7th bit would be 1. And that makes sense. So once we figured that out, and again, this is some of these things looking at old protocols, you're not used to working at this level. Or at least we weren't. But you find this, and it responded. And then we were able to start decoding the messages because we, again, set all the values to known characters. So I've abbreviated this because this is actually from my notebook when I was working on this. And we were getting so many different dumps from the ATMs that we were just trying to abbreviate it. So it's start a character, then it goes terminal ID, field separator, the encryption code, I believe, the field separator. We couldn't identify 1 byte or 2 bytes. A field separator, ETX, and then the LRC. As it turns out, a lot of the protocol fields are optional. So what you think might be a required field is actually just optional, and there's the only indication that it is required is that if you have more bytes than you expected. There's no field headers saying this is a required byte, which is really confusing. So we had to actually account for, if there's just extra bytes, redo the processing completely. So we started doing things to try to process the data, and we finally ran into one final challenge, the LRC. Again, this is where there shouldn't be a lot of opinions online on how an LRC is implemented, but as it turns out, there is, for a single byte. If you're doing a 1 byte LRC, there shouldn't be a lot of opinion on how this is done. But as it turns out, there are a lot. And a lot of people are misreporting CRCs as LRCs. And they're not exactly the same. One uses a table, the other one does not. So it was a lot of time wasted, but we kept getting 0x95, and because of the parity bit, that's actually NAC, which is hex 15. So once we got this all communicating, the ATM wanted something from us, and we weren't sure what it wanted. Well, it turns out it wanted the host download request and the host totals request. The host download request identifies the ATM. It says, hey, I am, and it says its ID. You reply with a set of encryption keys. Encryption keys are very interesting in this. It supports a maximum of triple DES encryption with a left-right key buffer. So you can have half the key actually known, so you can use it to have multiple payment processors on a network, or on dialing out, which is interesting. It's a 64-bit key. The standard is X 9.8, which actually describes how to send a 64-bit key represented via ASCII. It's kind of interesting that it is a standard, but it is. So we were able to implement that. And we used our simple one-key structure. So we then got data. And this is from the actual original processor. And it's really small, but you can see that it receives the message where up here is the terminal ID. And you can see the offsets that I'm processing. And then down here, it sends the encryption key. And then the ATM still was angry. Well, one final point. Remember I said it needed a host totals? Yeah, see there's the 15. We forgot to send the host totals. So host totals sends the date and time. It's like NTP with fee calculations. So it sends the date, time, and fees that the ATM has to send. And so if you've ever used an ATM out of network and it says in the little bottom, it says 50-cent fee or $1 fee, that's actually set via the ATM when it's initially connecting to the processor. So if it's unplugged, reconnects, it downloads that only once or during an update state. But we realized, okay, we're doing all this implementation in linear code, which was very hard to do. Like this is not a very, protocols like this are parallel, so it's very hard to, or not parallel, but they're states. And as you're guessing, it should be a state machine. Doing it in a linear fashion is very bad. So we built state machines. And this is the eventual, what we reconstructed on how the ATM worked. So it took a very long time to build that model. But with that, it allowed us to take code that looked like this, and I'm just showing you the count, you don't need to read the code, into something that actually has handlers and can call messages and process them. This allowed us to build, as we discovered new messages in the protocol, to add support for them. And this happened quite a lot. So you can see, here's another message print from the ATM, and it succeeded. So when it finally gets, when it's less angry at us, it actually says this. And so now we have a working ATM. And once the host totals were processed, we were good to go. That gave us a design decision choice on how we were going to implement this for the competition, of course. And we decided that all host downloads and host totals would be run on the local payment processor that we built. And all the other requests would be sent out to a centralized payment processor. We don't know if this is how it really works in the real world, but that's how we did it. So first test run. It's processing. So there you go. We also discovered another thing. We're not rich. We can't load this thing up with the $220 bills that it's designed for. So we went out and got monopoly money, essentially, fake money that you can use for costumes and stuff like that. It does not like that. It's designed and weighted for real money, real currency. It turns out that if you need to get weighted currency that's the same weight as US money for doing something like this, Jamaican money. It's the same weight, size, and everything, texture, everything, and it won't get shredded. We learned that one, so that was interesting. But in all, there were 20 different response messages that we had to figure out from this machine. We used only 8. Response messages are after it does the transactions, what it says in responses. So 0 is true, 1 is false, as you can see, but there are 3 1s and 3 zeros. 19 is an error, and it just goes on and on. On these ATMs, only one track of data is processed, track 1. Track 1 is what actually contains your credit card information. Track 2 actually contains your name and other information. It's only taking the raw credit card, or debit card, as the case may be. Padding is kind of interesting. $20 is floating, but in ATM world, it's 002000. And if you misalign the zeros, you get a very different number. And that's also why there's 10 reasons I shouldn't be an ATM processor. And also I will point out that the terminal fee is equal to the amount that you request. So if you request $20, your fee is $20. And if you request $100, your fee is $100. It's a really economical ATM. So another little fun video from getting it working. You can see the code working. And dumping out money. So I don't know why it's doubling up on the videos, but we're going to switch gears for a second. Because as I said, this is an embedded track. You know, everyone's here probably because they want to hear about the hacking, but ATMs like this still exist. The fact that we could just buy them and they were used as recently as last June means that these ATMs still are in use. These are products that were built by some engineer probably, 20 years ago. Talk about longevity. You get to see your product everywhere, and still, it's almost like the Windows XP background. The guy who took that, he still sees it everywhere. But that means that you have to design something for embedded that lasts a long time. Is the design of your system that you're putting together actually capable of handling that? What type of Linux are you running? If you're going to be using Linux, what are you planning ahead? Are you taking into account that maybe at some point you're not going to be able to update the system and you're going to run out of resources? You're going to have it stuck. How are you hardening that system? So, people need to make these things more modular. I was saying there's a whole business of just replacement parts, but they're expensive. When you're designing embedded systems, maybe the plan is to make them modular. I was looking at Omniturus, or Turris, I guess is the company name, but they actually have a modular router that you can just swap the components, and you can keep the Ethernet part and upgrade the main core. So modular designs like that are good. I know they're very out of reach for most companies, but designing something where you can have either a service technician upgrade or provide that support is very important, because otherwise you're going to end up with these ATMs which are still running 16-bit processors, which in and of itself is not bad, but the fact that they still are using 3DES and or triple DES, and they're using SSL. Like that should be not allowed at this point. It should be easy for a user of your product to get updates. And then let's get to the protocol. The protocol is another interesting legacy product. It's 40 years old at minimum. Maybe a little newer because they have revisions. But that means that this protocol was designed for an entirely different world, a dial-up world. It's now being encapsulated in many cases over a 4G antenna. And in some cases, they've actually improved it so it's actually using more modern communication methods. But let's just talk about the one that still exists, that it's really out of date. It's plain text for 90% of the transactions. Someone can just intercept and adjust the amounts, and all the data is sent over almost plain text. Some of the data, the PIN key is encrypted, but if you get the credit card number, does it really matter? How many places verify the PIN? You can just do a transaction in many cases. So there's issues. And in this case, one question I have wondered about this protocol is, why was the whole message not encrypted in triple DES? Sure, it's easy to break, but as someone looking at this protocol, I would never have been able to easily implement it if it was actually encrypted. So, let's work towards more secure systems. Use standards that are going to be around for a while, and that you can easily switch around. I know that's not a cure-all and be-all for everything, but use things that you can maintain, that aren't going to, like, even the most legacy web server these days is still around. You have protocols and libraries or not protocols, but you have libraries that are designed to support newer encryption methods. Like, look at Arduino. It can support pretty much any modern encryption standard for web requests. If this thing was using a more open protocol, in theory, the firmware could be upgraded to support that. So, plan ahead for using as many open standards as you can. And, if you're going to be doing protocol analysis, take some of the tips. You're going to make mistakes because you get into this little zone where you're stuck working at things and trying to figure out the fine details, and sometimes you're too into the protocol to realize you need to just step back. And of course, if you're implementing these again, just plan ahead. These things are around, and there's a lot of protocols like this. Think of Modbus. That the solution for Modbus security is isolated as much as possible, and that we can do better than that these days. So that's it. Hopefully you guys have had a fun ride with getting ATMs working, as I did. And you can follow me on Twitter, and happy to answer any questions. Sure.
I'm curious, from the project, just in balance, how much would you say was reverse engineering? Which is to say, if you had complete documentation to have to figure out something that should be documented, what percentage would you say was reverse engineering?
The amount of pure reverse engineering, because we were getting fragments of documentation through the whole thing, I'd say it's pretty small. But the actual implementation of the protocol, by happenstance, we were able to find some of the protocol guide, provisional one. So we were able to take that and modify it into what the actual protocol was. So there's still a lot of effort. But the fact is that for all these systems, there's quirks that aren't documented. None of the stuff followed one-to-one with what we had found. So there's a lot of work in getting the components to actually work. So it's not a huge amount of reverse engineering, but it's a lot of researching and tinkering. So yeah. And any other? Yeah.
Who was the manufacturer of the currency reader for the ATM?
The currency reader, as far as I know, they were all part of. Oh boy. I'll put up the.
Red currency.
Well, it has a light reader on a reader on the machine to see if it's get the bills. Where is there it is. So as far as I know, all parts were for or through Hyosung and Tranex. So it's going to be whatever vendor and design for that. So you got your EMV card reader, the currency dispenser with its basic checking, like to make sure the bills are coming out. The screen was its own group of components. The printer was its own group of components, and they all communicated over serial for the most part.
So you guys, one of the areas where devices like ATMs were talking about the casinos, right? All slot
Yeah.
machines and gaming devices have currency readers and ticket writers and all that kind of stuff. Did you test the currency reader with your Jamaican money or any of the other devices and accept it?
So again, the reader is more just in this machine was just to make sure that the machine was dispensing money, rather than actually it was just seeing money's here, okay, and because if it had an issue, it would actually lock the ATM up and say error, and it would try to do a reversal, and then undo the transaction. But I'm sure in more advanced, more modern ATMs, there's actually a reader checking and accepting money. These only allow to dispense money, and so they're only tracking the currency that's in there. Yeah, any other?
You mentioned that the ATM worked just with the card number. So is the PIN simply to unlock the screen, or how does the PIN?
The PIN is transmitted encrypted, but the card number is transmitted plain text. Yeah, it's an interesting design choice. I'm sure there's a reason for it in VisaNet, but that whole thing is transmitted to the payment processor. In our case, when we built our payment processor, we decoded the PIN and ignored the PIN because for this competition, we didn't have to worry about any of the actual processing of real data. We had cards that we wrote to, and they weren't real credit cards.
Right, my understanding is the PIN is not stored on the card, so the processor then said, okay.
Oh, it's sent. Yeah, you are correct.
The machine's okay to expose the account.
Yeah, you are right. I misspoke on that. The PIN is entered by the keypad, and it's sent along the protocol with the credit card with track 1. Sorry, yeah, that I did misspeak on, is that the data. Well, I was thinking in the world of the protocol again, and it sends that the PIN encrypted and the track 1 card number through. So, yeah.
Any surprises on the physical security side?
Physical security wise, these things were monsters. They they are if you know, they show videos of people just walking off with safes, and I literally have no idea how they do it. These things, it took 4 of us to move them with a dolly, each ATM, to get them set up for the competition. My favorite thing about these was when we had finished the competition, there was a class in the classroom following the event. We forgot to take them out because we were just so tired. We're like, okay, we'll get them the next day. And they're like, oh no, there's a class. And so these students came in and they're like, and we're trying to get, we walk in and they're like, hey, do you know why there's an ATM in the classroom now? And we're like, no idea, just walked out and waited for the class to end. But it was pretty funny. But these things are heavy. They require a lot of effort to move. And so physical security wise, they're pretty good. You could bash this thing pretty well. I don't know what you'd do because, you know, you can wire into the front panel, but it's going to be pretty obvious. And these places are usually not, you know, easy access. It's or they're easy access. They're high traffic, so you're not going to be like, okay, just wiring into the thing to get it to release. And it also is speaking of serial protocol, so you have to know that protocol in advance. So it's fairly physically wise, well designed. It doesn't support EMV, but again, that was an upgrade that you could go through. So, any other questions? All right, thank you guys. Hope you guys enjoyed.
Completely off topic, but
Oh, what?
we're getting a little bit of,
Check 1, 2, check. So your choice between the lavalier microphone and the handheld. Power button is right here, if you choose.
Okay.
And I'll check back with you. And you found the HDMI cable and Type-C? I think it's like mini. It's not. It's one of those, but it'll go right to the projector. I'll take your hand if you have any trouble. Thank you so much. Let's see what happens. Oh, that's not at all what I want to show you. Great. Feels like they're in the right place? Am I in the right place? All right, that's a good start.
I'm in the right place.
Good, that makes two of us. All right.
I'm different.
that works. All right, we'll give people a few more minutes since it's right after lunch. It's funny, how many people were planning on doing the SCaLE training? Anyone? Yeah. Those poor guys. I did it like 3 years ago. It was great. I guess those guys got stuck in foreign countries and couldn't get flights and whatnot.
They going to put on another show, or
Sorry?
are they going to give us another chance to do this, or?
The SCaLE training?
Yeah.
I suppose it'll be back. I think this would have been their third or fourth year here.
Because I want my money back. I want them to show up and teach me.
Oh, I assume you'll get a refund.
I don't want to be fun. I want them teaching me.
Right, well, you can apply to next year, I guess.
Yeah. Right.
So I'll burn another minute or two. How many people are familiar with microcontrollers? Oh, okay. Good. So I can skip to all the hard stuff. Actually, this is more of a survey. It's kind of like high level. I try to cover everything that's going on.
I'm familiar with them, but I've never done anything with them.
Oh, and at other conferences, I do a follow-up class to this, or session to this one, where I talk about actual coding for microcontrollers. It's more about, yeah.
Let's say, ask, like a sample as to where people are and where the pain points, and maybe we'll kind of
Yeah.
tune.
Well, we might get to that. I have a lot of material, so I'm just going to kind of fly through it, and I'll have the slides posted. All right. Can you hear me now? Oh, good golly, the thing's loud. Is it loud? Yeah. Okay, I'll try talking here. I talk pretty loudly, but I think they need this to record it. Oh, well, someone closed the door, so I guess we're officially starting. Well, welcome to Microcontroller Architecture for Embedded Programming. I'm Todd Siebert. And as I mentioned earlier, this is going to be something of a survey of the architecture of microcontrollers, and a little bit of microcomputers, and how it relates to how you may get things done on them. And I'll post the slides. I'll have links later. So, people talk about embedded. What is embedded? Basically, embedded is any time you put a microcontroller or a microcomputer inside of something such that its activity is secondary to whatever it is that people see on the outside versus going to their laptop or desktop. You may not know this, but modern cars have approximately a dozen microcontrollers or microcomputers in them. Well, I guess it depends on how you measure it, right?
Separate processors.
Yeah. Yeah, they're just riddled with them. Your washing machine, thing third from the left is a Tickle Me Elmo if you take the clothes off. Frightening, isn't it? All modern cameras and whatnot. So what is a microcontroller? A microcontroller is often referred to as an MCU because it's got fewer syllables, right? Or the little mu C symbol, and microprocessors or MPUs or UPs. Generally, microcontrollers have less RAM. They have less of everything except I/O, generally. And generally have some kind of storage right on the die. Or RAM, that is. Microprocessors generally deal with RAM that's off the die. They'll have, you put your RAM sims in or whatever they use now. And then we get into cases like SoC, system on chips, which have some of all of it, what you'd normally find in a computer, like a desktop computer, jammed into one package. We'll get more to that later. I covered this. Basically, they're slower generally. They're simpler in some ways. They can be much less expensive, anywhere from 3 cents for a microcontroller up to like $20. Generally, they don't run an OS, although they can run a real-time operating system. There's different types of memory in them that sometimes comes up when you're trying to program them. I'm not going to get into this too much, but there's Harvard and von Neumann. You may remember that from your college computer science classes, and you were like, why is this important? It becomes important when you're doing microcontrollers. I'm skipping through some of these because we have a lot to cover, and I suspect there'll be questions. Some microcontrollers offer protected address spaces, memory management units, things like that, or privileged execution, like you might find in a regular microprocessor that runs a regular OS, but many times they don't. So if you have code running in different places, you have to be careful you don't write over your own memory or write over your own code, depending on the architecture, because there's no one to stop you. Which also means if you're trying to secure the device, to make sure no one else can write over, because they can make your code do whatever they want. Program memory generally is non-volatile. Usually it's flash or EEPROM. RAM is generally faster, so some microcontrollers will copy the program into RAM. If they have enough RAM to run it from there, it's faster. So on a microcontroller, instead of the whatever, I think my laptop has 32 gigs of RAM. They usually have like 16K to 128K is pretty common, which means you have a whole different idea of how you're going to code. Data memory can be anywhere generally from 8 kilobytes to like 256 kilobytes, which isn't a whole lot, And some have non-volatile RAM where you can store stuff if you like lose power or if you're trying to keep logging data, things like that. But usually it's very small. Oftentimes you're going to want to put that off chip anyway. Instruction clocks. Okay, we don't have generally 4 gigahertz microcontrollers, but they can get up to like about 1 gigahertz, sometimes higher, but speeds more like 40 megahertz to like something like that is much more common. So you don't have generally the raw processing power you would. And for those who don't remember, if you have like a 16 megahertz clock, a cycle, which becomes important when you're programming for these things, is basically the reciprocal of the clock speed. So a cycle for a 16 megahertz clock is 0.025 microseconds, which doesn't seem like a lot, but it becomes timing becomes important when you're doing certain things in a microcontroller. Oh, especially since every instruction a microcontroller runs can take usually more than one cycle, can be as many as a dozen or more. Like microprocessors, some microcontrollers are superscalar. They can execute multiple instructions per once. Sometimes even have pipelining. You may not know what these all mean, but as you get more powerful and these different architectures come into play, your microcontroller becomes less deterministic in its timing, because you don't know necessarily how long each instruction is going to take. Basically, this is about speed and performance. Not that important right now. Instruction set. You know, even like something like division can take 17 cycles, so that's quite a while. It gets expensive, especially if you have a small microcontroller. There's ways to get around this, lookup tables, approximations. There's all kinds of algorithms out there you can implement if it doesn't actually include like subtract or divide, or multiply or divide. And then like things we always use in computer science like module, it requires division. It's not easy for a computer to do, or a microcontroller. Floating point math, pretty rare in microcontrollers. Again, you have to come up with algorithms to kind of get around it. I've mentioned one called binary scaling you can look up. Sometimes they put floating point units on like what's called a peripheral or a different part of the chip, and you have to context switch just to get the math going, so there's a cost to the context switch. So you have to decide if it's worthwhile. Microcontrollers have endianness, which is important if you're trying to transfer data between devices, because you have to make sure they have the same. It's basically which byte is first, the least significant byte or the most significant byte. You know, if you're doing desktop development, this never comes up, essentially. Okay. Physical aspects. How am I doing on time? Actually, I'm going through this pretty quick, so if you have any questions, stop me. Okay, so some definitions. An IC is what's on a die. It's a piece of silicon. Here's a blow-up of an Atmel AT Tiny 13A, which is a really simple microcontroller. Obviously, they're made of, there's various sections on the die, and each section has all kinds of circuits made of primarily transistors, and each transistor is, etched into the silicon to comprise logic gates, and that's what makes computers work. The package is what holds the die. So you can get tiny, here's a PIC 10F and a SOT 23 package, and you can see it's kind of small. So you can put these things in anything. Here's one of my favorite, which is an AT Tiny 85. It's an 8-pin DIP, dual inline package. And then you get these gigantic ones that look like desktop processors with hundreds of pins, which are also nearly impossible to solder if you're like a hobbyist. So how do we get more supporting components and associated things into a chip? Well, there's different solutions. We have something called the system on chip, SoC. Basically, they put everything on one die. The CPU, RAM, everything else they can. That basically is logic-based. Then they came up with basically multi-chip modules. Basically, they put multiple dies in the package, and they stack them. They put them side by side, and they connect them with tiny wires. And the little chips inside of things like that are called chiplets. And we'll talk more about that later. Then there's system in package, SIP, and they basically stack the dies vertically, which saves space, and you can put more in there. Then you get SOPs, system on package. And like these terms, like it's so confusing why the industry came up with them, but they are what they are. And the nice thing about the SOPs, it can include discrete components like capacitors and inductors and antennas. So you can basically have everything in one package and basically just connect your I/O and your power. And then there's something called a customizable system on chip, which generally is a subset. It includes an FPGA, thus the customizable part. We'll talk more about FPGAs later. So as a simple side view diagram, this is what they look like. So you can see, can you see my cursor? Yeah, you can, nice. So you can see in SoC, everything is side by side. And in MCM, these are the chiplets, like this little box here. You can put them side by side. And you can see there's wires going through the substrate. And then system in package, they stack them vertically to save space, which means, but things have to be connected vertically instead of going through the substrate. And SOP, they kind of throw everything in there in whatever way. The result of this is, whereas a chip used to do one thing, now it can do pretty much an entire computer in a package, or Wi-Fi and communications and things like that. Here's an example of the. This is the TI SIP. This is the one they use in the BeagleBone Black, I think. I thought I wrote that down. But it's nice because it actually has an ARM Cortex-3 microprocessor and two of these PRU, programmable real-time units, which is basically a microcontroller with a deterministic instruction set. And it's all in this one package, so you can just pop it into your designs or into your breadboard, whatever you're doing. Yeah? Well, okay. So yes, interrupts can definitely throw off your deterministic, but microcontrollers used to be basically every instruction took so many cycles. So you could just, if you needed something to happen like every 24 cycles, you knew you could only get 3 instructions going, right? But now with like pipelining and SuperScaler and different instructions taking different number of cycles, it's hard to know how long something is going to take, because even if you counted the instructions and amount of cycles they take, with SuperScaler and pipelining, like, you don't really know. It's kind of up to the chip. But with something like the PRU, you know everything. There's no SuperScaler. There's no pipelining. Everything is the same number. But if you program using interrupts, which is generally a good idea, do you have to take that into account? So I will talk about that a little. But many things in a microcontroller come down to timing. And if you don't know how things are timed, then it gets even more complicated. So you can see this down over here. It includes EEPROM. It's got a LDO power. Anyway. Okay, so I think chiplets are really exciting. There's been a lot of talk about them over the last couple of years. They can use them in MCMs, SIPs, and SOPs. And that means they're basically commodity, tried and true, reusable, cost-effective pieces of silicon that do one thing, basically. Either it's the memory, or it's a cache, or it's a logic block, or it's the processor itself. And basically, kind of like Legos, you can kind of stack these things in a package and get basically whatever you want out of that chip. And since you're not trying to make this huge piece of silicon, which gets expensive and you have more of a chance of a failure, because you've had this big piece of silicon, if you break all the functions up into their own pieces of silicon, you have a much better chance of having higher yields and lower costs. So manufacturers are pretty excited about this. There's been some issues about durability and manufacturability, and like all the vendors have their own standards, but we'll talk more about that too. Oh, right now we'll talk about it. So the Open Compute projects, Open Domain Specific Architecture, ODSA, started in 2018, and basically they're trying to standardize how all the chiplets talk to each other. It's basically similar to an OSI ISO model, if people remember that from way back when, probably comp sci class or whatever, or networking. This way, you can basically take cross-platform, cross-vendor commodity chiplets and get them all to talk to each other, which basically means you can make any chip from whatever parts you feel is best. And then the Linux Foundation started the CHIPS Alliance way back in 2009, and they're more about making IP available. So you have a quote here: organization develops and hosts high quality open source blah 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 IP and interconnect IP and open source software. I don't know they're making a lot of progress, but it is promising. And so this way, not only will you be able to have a chip, but like all the components in the chip will be open source. Because we talk about open source, there's like a couple vendors upstairs with like open source laptops or open source routers. But when you get down to it, the chip isn't, right? But we're moving towards a time when that's actually possible. And even Intel contributed the AIB, a royalty-free physical layer connecting semiconductors in a die. So even Intel, I was surprised. And there's like a company called ZGlue, basically offering custom MCM chips in small batches. So theoretically, if you had you're an IoT vendor or even a Kickstarter, could theoretically order, I don't know, 1,000, 10,000 custom chips based on, maybe if you got lucky, maybe all open source chiplets, maybe close soon. We'll see. But I think that's pretty exciting. Okay. We're talking about something different. So, in a microcontroller, we have something called peripherals. And a peripheral is a type of interface that's on the die itself. And the interesting thing about them is they run independent of your code cycles. So even if your code is doing something and you have a PWM, that's a pulse width modulation, going on, would be a peripheral, running on a pin at like 50% duty cycle, it keeps toggling back and forth regardless of what your code is doing. So it doesn't really cost you anything. So it's not really multi-processing, but they run independent. And there's lots of different peripherals that can show up on various microcontrollers, analog digital converters, DACs, serial peripheral interface. You probably heard of a SPI connector or SPI bus. There's TWI, two-wire interfaces. These are all communication types. sound interconnects, USB, Ethernet, Wi-Fi, I'm sure you're all aware of. All these things can be on the die or not, depending on the microcontroller you buy. I feel like I skipped. No, I think it's coming later in the slides. Timers and counters are really common peripherals to have. They're great, again, for timing if you need to know when some kind of time has passed. Control area networks. That one's popular in cars, as we talked about how many dozens or maybe hundreds of microcontrollers they have in modern cars. Real-time clocks, GPIOs, that's general purpose I/O. Various memory interfaces, and as I mentioned before, floating point units, possibly comparators, UARTs, which is basically the serial communication, watchdog, and another communication protocol called OneWire. Some special purpose microcontrollers have all things from different memory controllers, crypto units, graphics, infrared, motor controllers, you name it. If some manufacturer thought there was a market to put some kind of peripheral on a die, they've done it. And there are many. Generally, as microcontrollers get more expensive or larger and usually faster, they include more types of peripherals and often multiples of each. It's not uncommon to see 2, 3, 4 different UARTs, a couple of SPI buses, dozens of GPIOs. But some microcontrollers have as few as 6 pins, and you get like one because you just want it to do one thing. I kind of covered this. Generally, each peripheral is, and historically, they were tied to one pin. So like that one pin did a GPIO and maybe it did something else, but that was it. And if you had to use that pin for GPIO, but you also wanted it for UART, you were out of luck. Most of the ones we're seeing newer have like what's called crossbar or matrix allocations, so you can basically assign a GPIO to whatever pin you want, which also makes board layout easier because you don't have now a GPIO pin on the wrong side of the chip from where it needs to go. I don't know how many people here are familiar with board design, but it can be a real pain in the neck. Now, if you don't have a peripheral and you want to do like, say, I2C or a UART, and you just have GPIOs, you can do something called bit banging, which is basically timing all the signals you need when you need them to happen, and basically reproduce the entire protocol in code, which for things like serial and UART is pretty easy. If you want to do I2C bit banging, find a library because it's really easy to get wrong. And this is where things like deterministic becomes into play, because if you have to really pay attention to get the timing right. And to her point, like if you have interrupts, keep interrupting your machine, you're not going to have the timing right. So if you need the peripheral, it's best to get it on the chip. But if you have to, you can bit bang it. Any questions so far? I feel like I'm covering a lot. Sure.
So if you have a microcontroller that has the PWM, you're saying that that's not from the microcontroller itself, that's
No, the peripherals are on the die.
on the die, but it's like you're not using duty cycles to do that PWM modulation.
Right. You basically, we'll talk about memory mapped. Most peripherals are what we call memory mapped. So how many people are familiar with Unix device drivers? Okay, Unix stuff is file mapped, right? If you want to get I/O, you write or read from a file. On a microcontroller, they're memory mapped. So there is no file system, right? So all you can do is there's a part of memory, and there's some byte someplace, and it's all going to be in the data sheet, which for a microcontroller can be like 1,000 pages, and I'm not exaggerating. You'd write to a particular byte in a particular bit, and say you want to make a GPIO output, or in this case a PWM, let's say. Now, and they all vary across manufacturers and across lines. So theoretically, you could say, okay, I want this pin to be a PWM. I'm going to, flip a bit to enable it, and then I'm going to flip another bit to say it's an output, and then I'm going to flip another bit to set it into a particular mode, and then I'm going to write to a byte, like say 128, to make it a 50% duty cycle, and then you're going to have to write another byte that's going to be like the frequency, and there's probably clock dividers and things like all you need to do, write all that, and then suddenly you have PWM. But once you write all those bits and bytes, it just keeps doing it. Yeah. I know that was probably a lot. Wasn't planning to get into that, but no, it's quite all right. Yeah, cool. And I do a second section where I get more into the coding. So speaking of pins, here's the ATtiny85, one of my favorite little, I use it for everything type of cheap little microcontroller. And you can see like here, pin 1 is PC interrupt 5. It's also the reset pin, also ADC 0, and I don't remember what DW is off the top of my head. So this one has multiple 3, 4 different functions available on each pin. So to kind of like the last question, if you want to use that particular pin for a certain thing, you have to go tell the microcontroller it's for a particular thing. And then there's lots of bits. And probably people have heard of, oh boy, on the spot. I'll get back to it, I'll think of it. And this is a simple microcontroller. Oh, I know, Arduino. How many people are familiar with Arduino? Right. So, it's C-ish. It's really C, C++, but they make all these macros. And these macros allow you to set set pin 1 to be output, right? Well, it's just a macro. And what it's doing is it's flipping all those bits and doing if you want channel 1, it's got to map channel 1, or pin 1 rather, to a particular memory region, and then it flips all the proper bits. And it does it all for you, but like in your code, you just write, pin 1 output, right? And all that, the guts is hidden below, which is nice because it's a nice level of abstraction if you're kind of just getting into it. But you can do all those things. You can write Arduino code without using any of the macros. You can just write it in C, but you just have to look up what all the bytes are. Okay. Here's an ATtiny828, a little more complex. Here there's lots of different pins doing lots of different things, and they've color-coded like power, analog, or a serial interface or a timer. And then you get this TI, I think is the same TI from the Beagle Bone, one of the Beagle Bones. And here they don't even try to put all the different peripherals available on each pin because it just becomes unreasonable. But at least you know which pin is called what. Okay, power management. I suppose you have a laptop, you're concerned about power, but if you have a desktop, it's just plugged into the wall. No one really cares how much power it takes. If you have a microcontroller, most likely, it might be battery operated. If it's running on a coin cell, you have to really be cognizant of how much power you're drawing. And I guess we should be green and we should be, keep this in mind somehow. But depending on the microcontroller, they have various states. They have like low power, sleep, and really it depends on the vendor and the product line. Sometimes you can change the clock speed. But you can usually get them down to really, really low, like in the tens of nanoamps. So when these things go into like these low sleep states, they can really take, almost nothing at all. I've seen people run microcontrollers on the coin cell for a year because it only wake up when it needs to wake up, usually via an interrupt. And then you have to pay attention to what peripherals, because in certain states, certain peripherals will be not available because they take too much power. Or you might have to do certain things, like you want to, some peripherals will just draw power. Like if you set up a pin pull-up, and it's going to take power because you're doing a pull-up. Everybody know what a pull-up or a pull-down is? Okay. So generally, if you have a pin and you send a high out, it's high. 3.3 volts, 5 volts, whatever happens to be, 1.8 volts. If you put low, it's 0. But if you don't do either one, it's basically an indeterminate state. And if it's in an indeterminate state and someone tries to read it, it could be anything. It could be high, it could be low, it doesn't matter, right? It depends on inductances and all kinds of things you can't really control for. So you have to pull up or pull down the line, usually with a resistor either to your VCC or to your ground. And that way you keep your signal in a determinate state. There's the 30-second version. Some microcontrollers have the lovely ability to be put into a sleep state, and unless you've remembered to tell it how to wake up, it won't. So that's probably good to remember. Anything else on that section? Any other questions? Okay, programming. This isn't like basically how to program one, but like physically how to program one. Because you can't just like load a DVD or call up your editor on the microcontroller. At some point in time, we had to like erase them using UV light sources and crazy crap like that. But nowadays, generally all you need is a USB to TTL serial adapter, like the one pictured, and they're cheap, even if you buy a name brand. And then you got development boards like the Arduino, which you just plug a USB cable into, so it doesn't get too much easier than that. Then there's something called an ICSP, in-circuit serial programmer, or in-system programmer. Basically, they allow you to plug something into your board so you can program it if it doesn't already take like the serial to TTL or a USB. Because it used to be you had to remove the chip and put it in a special programmer, which probably cost a lot of money. But now, generally, they've made it a lot easier. Then there's JTAG, which is Joint Test Action Group, whatever, no one calls it that. JTAG. JTAG connector has some number of pins, and you can program and debug your code. I won't get into this too much, but the nice fun thing about microcontrollers is once the code is running, you have no idea what's going on in there. There's no console, right? There's no screen. I mean, sometimes it can be, but the vast majority of the times there's not. So there's all kinds of techniques you can do to debug them, but I'm not covering that in this talk. How are we doing on time? I got 20 minutes. Okay. Vendor-specific programmers / debuggers are available. Atmel ICE. There's a nice open source one called 1-Bit Square's Black Magic Probe for ARM. It's on the left. The microchip PIC programmers on the right. Nowadays, they're making it even easier to code. Like some of the dev boards, like from Adafruit, you plug them into USB and it mounts as a drive. And you can use your favorite editor to edit. Usually it's a Python or a CircuitPython program. You can edit it, and as soon as you save it, it reboots, it restarts the board, and your code is live. I mean, that's super simple. It's a good place to start if you're not already in this kind of arena. I mentioned debugging. Yeah, debugging gets funny. But in best case, you can do things like breakpoints, stepovers, watches, stuff like that. Like the Black Magic Probe is. See that thing in action, it is like magic. Oh, wait, I did talk about this. If you don't have hardware debugging, you can do things like writing to a serial connection, or toggling an LED, or driving a 7-segment LED display and outputting like an error code. The thing about this is they all take system cycles, right? So if you're trying to do something timing sensitive and then you take time out to write something to an LED, you're now messing up your timing, and it creates what they call Heisenbugs. Uncertainty. Okay, interrupts, briefly. Basically, they can be hardware or software generated, and they call what's usually called an interrupt service routine or interrupt handler code. Usually, microcontrollers are simple, like you have one interrupt, and you go to the interrupt routine, and you can't service another interrupt until you're done with that code. Other ones offer priority interrupts or interrupts within interrupts, but if you have to deal with interrupts within interrupts, then your brain will hurt. But then again, if you don't handle your interrupt quick enough, you may miss the next interrupt. So software interrupts can be generated by user code, Stack Overflows, part of your code throwing a software interrupt. And hardware interrupts are generally generated by peripherals, such as GPIO. Like, you want to know when data shows up, right? Or a peripheral, like your LED, your IR peripheral receiver has received data, and it wants to let your code know. How does it let your code know? It throws an interrupt, and you grab the interrupt, and then you go grab the data. Interrupt-driven code is basically how you want to do things. Otherwise, you have to poll, and you don't want to poll. So learn interrupts if you don't already know them. It's a little more complex, takes a little more effort, but it's the right way to go. Real-time operating systems are basically like kind of like the kerneling or scheduling portion of a full operating system that can run on a microcontroller to kind of help you out if you're trying to juggle multiple real-time, input outputs. Generally can't run them on the simplest of microcontrollers because they simply just don't have enough cycles. There's a number of commercial ones and open source ones. So, configuration bits. So they are often called fuses or fuse bits, and they're basically out-of-band, non-volatile toggles that change the way your processor works. Everything from clock speed, divider, watchdog timers, debugger enable, like a lot of commercial products you buy will have JTAG disabled, debuggers disabled, and it's a permanent fuse. So in the commercial product, they'll disable all that, so you can't go in there and hack it. Of course, if they do, you can't fix it. And if they do enable it, you might fix it or you can hack it. So it's a double-edged sword, I suppose. Yeah, there are DigiKey, which is a popular distributor of all things electronics, lists 76,000 different microcontroller SKUs. It's a little overwhelming. Basically, there's ARMs and MIPS. They license out their cores for other people to manufacture. I think the important thing to know about this is the IP that goes into a microcontroller can be used other places. I'll get to that later. And something called, but peripherals and hardware abstraction layers vary a lot. So you're always going to be reading through that data sheet. We have the microchip, Atmel, ATmega, and ARM variants, the ones you see in their Arduino products a lot. Microchip PICs. I know a lot of people were really into PICs for a long time. TI makes a bunch that are popular, like the AM335, which powers the Beagle boards. The ESP8266 and the ESP32 are relatively new. They're really great. They have Wi-Fi and Bluetooth. Especially that ESP32, you can do a lot of fun stuff. Parallax Propeller, although I haven't heard from them in a couple years, and a couple more. STM microcontrollers makes it really popular. STM8 and STM32 lines. Now it brings us to the RISC-V Foundation. People heard about these guys? Completely open source cores, all kinds of opcode extensions, and basically you can use them as long as you become a member of the foundation, which is, you know, a nominal cost. Is really great because all the chip designs used to be all proprietary, but now we have a real successful core that's open source. I kind of already talked about this. Sci-Fi is a company that's been producing a number of open source boards using the open source RISC-V processors. And everybody's getting on board. Like, not a week goes by where I don't hear about some big manufacturer like Western Digital, NVIDIA, Sager, Qualcomm. All these people have joined the foundation and are going to start using open source cores. FPGAs is the last section. Hopefully I'll have enough time. So FPGAs are field programmable gate arrays. They're basically a unique type of IC which basically allows you to change what the chip does because you can change how the chip is basically wired inside. How many people are familiar with FPGAs? Oh, okay, good. You all know. So this is a comparison to basically general purpose processors, which, you know, they have their own defined opcodes. They have, you know, whatever they do is the way you get it. But in FPGA, you can basically, quote unquote, reprogram to basically do what you want, how you want. And you're basically laying out logic blocks. You're not coding as in like C. You're fundamentally changing the way the processor routes data inside the chip from logic block to logic block. So FPGAs are used for development leading to ASICs or directly in products sometimes where you don't have enough quantity to make an ASIC or it's just not the right. There's no, out of those 76,000 microcontroller SKUs, it's just one of them just doesn't fit your needs quite right. Sometimes it's price. Or if you want to iterate, if you have a, you know, a new product and you're iterating on that thing a lot, FPGA is a way to go because you can just keep changing it. And I guess if you had a bug, you can fix the bug too, whereas if there's a bug in your microcontroller, it shows up in the errata and it drives every developer past that point mad. Yeah, always read the errata. So here's some history. The precursors started way back in the 1970s. There's different variations. I'm going to skip all this stuff for now, so we have time for questions. I guess the thing I point out about this slide is generally they're measured in logic blocks, and it comes down to marketing and what the manufacturer wants to do. Sometimes they're called LUTs or labs or CLBs or logic blocks. And everybody's idea of what a logic block is different. Like, how many NAND gates does it have? How many AND gates does it have? Well, it depends on the manufacturer. So you can't say, oh, look, this one's got 10,000 logic blocks and the other one's got 20,000 logic blocks. These numbers are not comparable. Okay, so FPGAs really started in the 1980s. One thing different from some of the precursors is they're basically a blank slate on power on. So you have to pull in their configuration from some external memory, some kind of non-volatile memory, and that's what makes the FPGA become whatever it is you want it to become. Everybody with me so far? Okay. FPGAs are programmed in what's called a HDL, hardware description language. And this is the type of thing that actually ARM licenses to the HDL, or not the HDL, but in an HDL, the design of the core from like ARM is what they license to other manufacturers who want to produce like an ARM core. And while some HDLs look like code, they're not compiled, they're not interpreted, they don't execute the way you might think if you're a coder. There's different HDLs like Verilog or System Verilog or VHDL. And there's a number of EDA tools, electronic design. I can't remember what EDA stands for, sorry. But the nice thing about FPGA is you can take your code and run it in a simulator beforehand. And you can do something called formal verification, which uses math analysis to actually guarantee that what the expected output is will actually be the output. I mean, we never see this in regular coding, right? So you can run tests, but this verifies it formally in math, which is a pretty good sign that it's going to work. Here's some sample Verilog, simply because it kind of looks like C, but it's not. The funny thing about most of these things is all the code happens simultaneously unless you tell it not to. So code execution does not go from top down or things like that. It all happens, yeah. It's hard to wrap your brain around. But it's really fascinating. Historically, all the FPGA toolchains were all proprietary, closed source, secret, and stupid expensive, and largely undocumented. But now we have something called SimbaFlow, which is a completely open source toolchain for programming a number of families of FPGAs, which is pretty exciting because you can actually get an open source core from RISC-V, and using an open source toolchain, put it on an FPGA. Now, the FPGAs so far are not open source, but we're getting closer. And I've talked to some of these guys. Like, the amount of effort that went into doing this toolchain is immense, because they basically had to reverse engineer bit streams. And this is a non-trivial task. So if you see those guys, thank them. There's a number of open source FPGA boards, like the Icebreaker FPGA, and I still have like 9 minutes, right? I think so. Kind of touched on this. Some processor cores, such as RISC-V or ARM, are available in HDL, so you can basically download that core to your FPGA and say, it's a RISC-V without a floating point. And then later you realize, oh, my application really needs floating point. You just go grab a different core, put that onto your FPGA, and now you've got all the functionality you need. So then if you're going to use like a microcontroller core or even a microcomputer core, once you get the FPGA running the core you want, you would then, connect to it and actually program it in C or load in, So there's really 2 steps. You have to program, quote unquote, the FPGA, and then you have to actually put your executable code on it. So FPGAs, basically, they're inherently multiprocessing because you can have any number of cores in there. As many as you want, really, that will fit. So they can be massively parallel, basically have any peripheral you could possibly want, flexible, as I mentioned before. You can reconfigure them. They're a little bit slower. Generally, they don't have the performance as a dedicated microcontroller. They generally take more power, and they're more expensive. But you can get them now, simpler ones, for just a couple dollars each, which is huge because they used to be like many hundreds of dollars. There's hybrids, like some FPGAs come with hard block microcontroller codes embedded in them, so you can't change that part, but you can change the FPGA part around them. And then now some regular microcontrollers have what they call custom configuration logic, or whatever the marketing term they have for that brand. And they have certain sections of your regular microcontroller you can configure to do certain things. So it's interesting how there's now like a spectrum of completely dedicated to completely flexible in various stages in between. In fact, even the new Arduino Uno Wi-Fi includes some custom configuration logic blocks in there. Oh, and that's me. So, I made it. Questions? Sure.
I know that like stuff like FreeRTOS can be downloaded to all the microcontrollers, which make the threading and the interrupts and all that stuff work easily. But they don't abstract any of the I/O. So if you're trying to, let's say, get something on SPI using DMA,
Mm-hmm.
you go to an ARM3 from TI to an ARM3 from Atmel, you know, everything is different. Are there any like libraries or things that we kind of like abstract the I/O?
So the question is, while RTOSs can help you with real time, especially when you have multiple real time things running, if you want to move your code from one microcontroller or to another, as I mentioned before, all the peripherals change, all the ways to access them change. So he wants to know, are there peripheral libraries that can be used, like abstractions that can be used across product lines? And frankly, I don't know of any. I mean, that's basically what Arduino does, right? For all the ones Arduino handles, of course, it's not an RTOS, but they abstract. So if you just set pin 1 to output, it has all these ways of trying to figure out which chip you're on, what is actually pin 1, and then flipping all the bits. That's why it's a little bit slower, because it has to do all this figuring things out. If you really think you might be changing microcontrollers or whatever, it's probably best to abstract in the code yourself, and then you can do like pound defines if you have to support multiple microcontrollers at the same time. But at least if you write your code modular and abstract all your I/O, at least you have a fighting chance later on.
But the learning curve, if let's say you're trying to have DNA and I2C from one machine to another, the learning impact is huge.
Yeah, agreed. The learning impact, even learning one chip and how to access all its peripherals. Now, if you're going to use like open source tools, and you're just going to use, the C compiler and just your favorite text editor and stuff like that, you're not going to get anything like that. But if you use like Atmel's commercial IDE, it usually comes with all kinds of bits of code and ways you can just drag and drop like routines to access like I2C easier, but it's all vendor specific. Yeah, I'm not sure if that helped, but anyone else? Okay, good. Well, hopefully I gave you a good overview of what microcontroller architecture is like and what you're facing if you get into it. And, well, thanks for coming.
Check 1, 2.